In this unit, we're considering functions that have multiple inputs, multiple variables as their input, and a more abstract example compared to our previous temperature model would be something like the ideal gas law from chemistry physics, physical chemistry. It's known that the pressure, volume, temperature, and number of moles of an ideal gas are related to one another. They have a constant relationship that's satisfied by this equation here. PV equals nRT is one formulation, or we can isolate the pressure and say that the pressure of this gas will be dictated by the number of moles, the ideal gas law, ideal gas constant, temperature, and the volume. If we're thinking of it in this direction, we would be imagining that volume and temperature are the variables that we're controlling, and pressure is the output. And V, T are the input variables, and under our control are known. That's typically how we interpret the input. We know what we can set V and T, or we know what they are, and we're calculating P as a result of knowing those two values. So this is clearly a function of two variables. And what we're going to do immediately is try to reduce it back down to 1 by doing the same thing we did in our last example. Keeping the temperature constant, say at 300 Kelvin, what is the resulting interpretation of the function P V 300? Well, it's going to be simply N and R times 300 over V. And that relationship of pressure versus volume is going to be an inverse relationship. Up here it's indicated that these are both constants. So we don't know them exactly, but we do know that there's going to be a relationship like so. Basically 1 over V, or a constant over V. And so we're going to get an inverse relationship. As the volume increases, we make a larger and larger container, the pressure of the gas inside that container is going to get smaller and smaller. So we can piece together the interpretation of this multivariate function, or at least get an idea of how it's working, by considering what happens if we keep one of the values constant. So with the graph, oops, I jumped ahead of myself there. The graph we would get would be an inverse relationship graph, P and V. And we're getting that, again, from that formulation. There are other examples in the textbook that are worth considering as well. What is important from that initial isolation of one variable relative to the others is that when we discuss functions with several variables, we often like to say, if we can, that our overall function, which has multiple inputs, in this case here, V and T, is how we're thinking of it. How is our output related to the individual inputs, one by one? In particular, can we say things like, is the pressure an increasing function of T? And what do I mean by that? If we increase T and we hold everything else constant, is it necessarily true that the pressure is going to increase? So we imagine freezing the world and just dialing up the temperature. If we do that, what happens to the pressure? So I want you to think about that for 1 second. All right. And I would say definitively in this case here that this is an increasing relationship. With all other variables constant or fixed, P is basically some constant times T. The nRT part is all going to be considered fixed or constant. And if that's the case, then an increase in T immediately means that we're going to increase P. Now, it's important to recognize that these are all positive constants, and there's a number of moles, that's the ideal gas constant, and volume is going to be positive as well. So yes, we're definitely going to have a positive times t, and if t is increased, then the pressure is increased as well. How about V? What happens when we increase V in this relationship? Well, I think our graph earlier told us this answer. If we fixed all the other variables, and here we're not being specific about the temperature, we just know that it's going to be positive in Kelvin. So with all other variables fixed, P is basically some new constant, K2, over the volume. We know the shape of that. That says an increase in V. That increases the denominator here, is going to cause a decrease in pressure. And again, this constant up top is certainly positive and the volume is certainly positive, so we don't have to worry about sign issues. But we certainly would get a decrease in the pressure if the volume were increased. And so it's definitely, our pressure is not an increasing function of V. When I increase V, I don't get an increase in the resulting pressure. Now let's make this a little more abstract. What if we have the function z is a function of x and y? So we would often write that as z is some function of x and y, two inputs. If we look at this formulation, is z an increasing function of x? I'll let you think about that for a moment. And again, it's going to let you think, but just remember the statement here. Does increasing x imply an increase in z, the output, with other variables fixed? Question mark. All right. Well, again, the way I would think of this is by treating all the other variables as fixed. So we'd have some constant out front. And most importantly for our analysis here, this would be a positive constant. And if that's the case, then definitely increasing x is going to definitely imply that z increases as well. So no matter what we do with x, if we make it bigger, z's going to get larger. So definitely z is an increasing function of x. How about the y side? Consider that, and again, phrase it the same way. Does an increase in y necessarily result in an increase in z? Well, our basic relationship, let's put a K2 here to distinguish it from the previous example. Our function would look like z equals K2 times y squared. If we were to sketch that out as a graph with y versus z, it's very clear that we'd have a parabola. And in here, we have z decreasing, whereas here we have z increasing. And notice actually that even this constant could be positive or negative, so we could even have two shapes depending on K2. This is K2 positive. We might have K2 negative, and in that case we would have z increasing initially and then decreasing afterwards. And all of this says that a simple increase in y implies an increase or decrease of z depending on a number of factors, depending on the x and y values. So very clearly here the answer is not simple like the previous case. In this previous case, if x goes up, z goes up. Done. Down here, if y goes up, well, z might go up if x happened to be positive and y is already positive. There's also many cases where an increase in y would make z go down. So we cannot make a simple statement like z is an increasing function of y in this case.